This is just a short part 2, one thing I forgot to mention in the previous portion of today's lecture, and also we'll take a look at the first problem from the lecture examples. I have it cast up on my screen. You'll just reference it from the handout that I've posted for you on Schoology. At any rate, however, I was talking about ohmic metals. Let me give you a brief description of what happens with non-ohmic metals. Okay, non-ohmic metals, if you plot current as a function of voltage, do not have a linear relationship between the two. In some cases, for example, you could have a curve, if you will, on this graph when we plot current as a function of voltage that essentially looks like this. Okay, a particular type of example of a group of metals that obeys this type of curve are types of metals that are referred to as superconductors. Okay, typically superconducting metals are metals that are cooled down to extremely low temperature. So when this happens, the interaction that occurs between the electrons flowing through the circuit and the actual atoms themselves that make up the circuit is rather minimal. However, mathematically, we don't have to worry about such metals here when you're introduced to currents in simple circuits, as we're being done here in chapters 25 and 26. The only thing that we have to worry about are ohmic metals anyway. Okay? Okay, and then we have the first example here from chapter 25. So at this point, if you wish, go ahead and pause the video and then copy down the first example. Okay, so the first example reads as follows. A 9-volt battery is connected to a light bulb with a resistance of 2 ohms. How many electrons leave the battery per minute? As we'll see, it's quite a bit. All right, so just drawing out a simple circuit here. Here's our voltage V. Here's our resistor, like so. And then we're given the following quantities. So V is 9 volts, and the resistance R, that's equal to 2 ohms. So immediately we just use Ohm's law here to calculate the conventional current itself. So V equals IR, solve for R. It says V over R, nothing more than that. So just 9 over 2, which is 4.5. So 4.5 amperes. Now this here is also equal to the amount of charge that leaves the battery per second. So let's just go ahead and let a minute elapse, and then we'll just calculate the total amount of charge that is left the battery when we do. Okay, now I'm not going to write this as a derivative for this particular example. Let me just write it in the following way. Let's write it as just a charge Q, and then divided by a time T. All right, so set the time T here equal to 60 seconds. And then therefore the charge Q is equal to the current I multiplied by that time T. So 4.5 amps, and then multiplied by 60 seconds, nothing more than that. Okay, and this comes out to be equal to 270 coulombs. So then therefore, if we take this and divide it out by the charge associated with an electron, that of course will then give us the number of electrons. All right, so the number of electrons is going to equal then 270 coulombs. And then we divide by 1.6 times 10 to the minus 19 coulombs per electron, like so. So coulombs cancels out here, and you just end up with a number of electrons. So divide by 1.6 times 10 to the minus 19, and this works out to be quite big, as you might imagine. It's about 1.7 times 10 to the 21 electrons, like so. So the amount of individual particles, if you will, that are flowing through a circuit in this manner, I, by the way, neglected to draw the current line here. Like so, the number of individual particles that are flowing at any one moment is quite large, as you can see. Okay? All right, so let me go ahead and conclude this for part